So as Niha teased this morning, this is a combination from active inference and integrated information theory that I've done together with, thank you, Jesse van Ostrom and Nihat Ay, and we're situated at the Institute for Data Science Foundation at the Hamburg University of Technology. So as a rough overview, although most of you will be familiar with these concepts, I will first roughly introduce active inference and integrated information, and then I will introduce you to simple simulated agents that we use with active inference on which we can then calculate integrated information. So I can give you at last a few preliminary results of our framework. So let's start with Friston's active inference framework. So most of you might be familiar with it. It's a unified way to look at perception, action selection, and learning as minimizing the variation of free energy. I don't want to go into the mathematical details of this variation of free energy, but only give a rough idea of the theory. So here on the right, you see a cat interacting with its environment, this little mouse toy. And the key ingredient in the active inference framework is the internal generative model. So the agent has some kind of model, some kind of representation about its environment that captures the dynamics of this environment. Here, the mouse looks a little bit different than it actually looks in the real life, but it captures the important parts for the agent. This is a perception part. And for action, we can combine the internal generative model with a prior over the actions and a preference distribution. So for example, if this cat would like the mouse toy to move, it would prefer to see the mouse toy to move. It can infer the good action for that, and the good action for that would to move its paws to slap the toy away so that the mouse toy moves. So there are a lot of different, there's a lot of different literature about the active inference framework. Here I put as a reference the book from Parr, Pizzullo, and Friston, Active Inference, the Free Energy Principle in Mind, Brain, and Behavior. So this was the first rough introduction here. Our second ingredient is the integrated information theory of consciousness. This was developed mainly by Giulio Tononi and it aims at assessing the amount and quality of consciousness of a system. They start with thought experiments, and from that they derive axioms about the nature of consciousness. I do not want to go into the detail with that, but more look onto the actual calculation of the integrated information. So here on the right, you have again a cat with this blue thingy with what's supposed to be a brain of a cat. And in the integrated information, what's important is at first that this is an intrinsic quality of the system. So it's really only about the controller, only about the brain. And secondly, it's not about what is represented in the brain, what's on the outside, but only about the causal mechanisms among the different parts of the brain. So here represented by this S1, S2, and S3. Although there have been different versions of the integrated information theory, so last year IIT 4.0 was published, the key idea behind measuring was stayed virtually the same. And it's summarized here by Giulio Tononi in his provisional manifesto from 2008. In short, integrated information captures the information generated by causal interactions in the whole over and above the information generated by the parts. So the idea is that we take a system, we cut it into parts, and then we calculate the difference between the whole system and the partitioned one. So this was the whole is more than a sum of these parts that we saw this morning in Nihat's talk. Now, of course, there are different ways in which we can do it. There are different ways in which we can partition a system. In the later versions of IIT, that can be very difficult with minimum information partitions, some minimizing, some maximizing. But in essence, it's partitioning the system. And then, secondly, there's a difference in how do you calculate this difference between the partitioned system and the whole system. So in IIT 2.0, for example, that was the KL divergence, and 3.0, the Wasserstein distance. And in 4.0, we have a new, or they have defined a new measure, the intrinsic difference for calculating this distance. We have in 2020 published a paper about complexity as causal information integration. And there we come from the information geometric perspective, and therefore we use the KL divergence, and I will define that measure in detail later. So now we have these two perspectives. The active inference, which is concerned with representing the outside world in an internal generative model, and integrated information, which is more concerned about the causal mechanisms inside the brain. And the question is, how do we combine them, or why would we combine them? So there's this paper that's already been mentioned by Friston, Wiese, and Hobson, where they look at the different axioms of the integrated information theory and conclude that they might, or they seem to be compatible with the active inference framework. And they even hypothesized that this speaks to the possibility of at least numerical analyses that show that minimizing variation-free energy maximizes phi, so integrated information, and vice versa. There has been a pre-study by Lundberg-Olsen et al., where they look at simulated agents, they call them animats, that evolve with an evolutionary algorithm. And there they calculate phi on the one hand, and the surprisal of the observation as a proxy for the variation of free energy on the other hand. And they see that with increasing fitness, the integrated information increases while the surprisal decreases. And also they see some connection between the phi and the surprisal where they both fluctuate at the same time. Here, we don't want to just calculate both of these, so phi and the surprisal, but we want to actually take an active inference agent, let it learn with active inference, and then calculate integrated information on that. And well, if you would think of pushing these two cats together, what's the natural approach? Try to calculate integrated information on the internal generative model. So let's look at more detail at the internal generative model. So the generative model aims at describing the relationship between the internal states. These are the states S here, the actions A, and the observations O. So here we have 3 time steps, t, t+1, and t+2. The time as well as the state spaces of the variables are discrete in this case here. And as you see on the right, there where we have the graphical representation, this internal model factorizes into the following parts. We have a prior over the internal states, PST. We have the connection between the observations and the given the internal states. And we have the transition probability between of the internal states of the next point in time, given the internal states in the last point in time, and given the action. So this is the internal generative model, and how do we now calculate integrated information? So first, we know that integrated information is an intrinsic property, so we should calculate it on the internal nodes, so on S. And secondly, as I said in the beginning, integrated information works by taking a system and cutting up it into parts. So we somehow need different parts here that are connected so that we can sever this connection and make a partial system. So our one additional assumption here is that the internal nodes actually factorize. So that we have, for example, 2 internal nodes in each time steps here, S1 and S2, and that they are fully connected to the last point in time. In this way, we can now calculate an integrated information measure. Now we will define our integrated information measure where we sever the connections between S1 and S2 through time. This looks like this. So the dashed connections here are the ones that we remove, and then we calculate the KL divergence between the full system and the partial ones. We call that the ground truth integrated information because in this case, we know all the influences that go into the ST+1, for example, here. So we don't have to deal with exterior influences as Nihat talked about this morning. So this is the way we calculate the integrated information. And now I can introduce the actual experiments. So we have small artificial agents. So this is a sketch of them. They have a round body. This is a blue thing here, and the tail, the blue tail marks the back. You can think of them as having two wheels. These wheels can spin either fast or slow. So they have 4 movements. They move fast forward, slow forward, turn left and turn right, and they can never stop. And the goal of these agents is to never touch the walls of their environment. They have 2 binary sensors. Here, these are the lines on the top with which they can detect walls. And in addition, they have the whole body is a sensor that senses when their body is touching a wall. So their goal is that this round body should not touch the walls. And then actually, the environment looks like this. So this is a labyrinth type environment where they have to run around, and the body of the agent is colored according to the action that they selected next. So these agents are now moving, this agent is now moving fast forward, turning left, turning right, fast forward, so on until it touches a wall. And now, additionally, the walls of this environment are sticky, so they are stuck. They can only turn on the spot here, and they can only push away from the walls when both sensors do not detect the wall anymore. So that now they can push away, and then they can move forward again. So now we have our simple environment, and we have our internal generative model with which they are controlled. And the question is, how do they now learn this internal generative model? Because we do not want to fix what the internal states actually represent. We want the agent really to figure out on its own what is important for its task, for what is important for it to store in its internal generative model of the dynamics of the environment. We can then apply approximate Bayesian update rules that were defined, for example, in the book by Parr, Pezzulo, and Friston, or also mentioned in the paper by Da Costa. The problem is, of course, that now we have a lot of different parts of this agent. And if we don't want to fix what the internal states are, we also don't have good priors. So if we just apply this framework very naively, without any additional assumptions, we get agents that do this. So here on the left, you see an agent that turns left, and it turns left, and it turns left, and it will go on just turning left. In the middle, you see the mutual information between the internal states and the observation. So this is a connection that is marked red on the right in the graph. So the agent, the mutual information here is close to 0.03. So very close to 0. What happened is that the agent converged to a very easy local minimum. They completely ignore what's going on in the outside world. They do not store anything important about the outside world in their internal nodes. They just select one edge action and keep moving in circles. It's not too bad in this environment. That actually works, but that's really not what we want here. We want them to really learn something about their environment. There are different approaches how we can make them learn better. Da Costa, for example, suggests that learning the generative model is on a different time scale than learning or selecting the actions. So that we would had to model when we would actually update the internal model and when we would just select actions. But we did not do that. Instead, we made the task a little bit easier for the agents by sampling the distribution, so the connection between the internal states and the observations. So the agents don't have to learn that. In addition, it's sampled, but they still have to learn the transition probabilities between the internal states. And this is actually the important part because we are calculating the integrated information on that part. And with this, I can now get to the results. So here we have 3 columns, and each column is for a different type of agent. So the first column is for agents that have 2 binary internal nodes. In the second column is 3, and the fourth column is 4 binary internal nodes. In each case, we have 200 agents, and these agents run around the environment for 50,000 steps. And then I calculate for every 100th step, we calculate the prediction error. This is the KL divergence between the internally predicted distribution over the observations and the actual distribution over the observations. And then here we see that I then ordered these agents according to this prediction error. So the further here they are here, the higher the prediction error, the worse these agents are. And here they have a lower prediction error, so they are better at predicting what their next step in the environment is. Next, here, a different approach here. We have additionally the success rate, meaning that we counted how often the agents are actually stuck at a wall of these 50,000 steps that they do. So a success rate of around 0.4 means that 60% of the times these agents were stuck, which is not too bad in this environment, actually. And we see that agents that were good at predicting the environment were also good at selecting good actions. So these two aspects of the active inference framework worked here together. And in addition, here we have the mutual information between the internal states and the observations again. This was the one that was 0 before in the agents that were just turning on the spot. And we see that these agents that were successful in the other regards were also able or have more of a connection between the internal states and the observations. And therefore, they are actually storing something about the environment. There is some connection. They are not independent anymore. So as a quick summary here, the active inference agents that predict their observations well also succeed in the task and form a relationship between the observations and the internal states. And now to the integrated information. That looks like this. So we see that these agents that were very good in the other regards also tend to have a higher ground truth integrated information. So here you see that these tend to be higher in these parts where they are good at predicting and they also succeed. I have to say that this is our integrated information measure. I've also tried the integrated information measures from IIT 3.0 and 4.0, and I do not get these clear results there. There are some relationships between the fluctuations. So fluctuations in the prediction error and fluctuations in the integrated information measures, but these are preliminary results and I would need to do further, or I have to do further analysis to really understand where these coming from and what the connection there actually is. So to summarize, we have these two concepts, the active inference and the integrated information, and we were able to push these together and to calculate the integrated information on the internal model of an active inference agent. And we saw that active inference agents that learn a good generative model and perform well also tend to have a higher ground truth integrated information. And as an outlook, this can be seen as a first step towards analyzing the type of generative model that can lead to high integrated information, so to a high complexity of a certain type that therefore potentially may lead to more conscious agents. Thank you.